Good day, ladies and gentlemen. We are now going to look at the mechanical properties of our metals. The importance of knowing these mechanical properties should be quite obvious. This will prevent the collapsing of buildings when steel is used as a construction material, and also of collapsing of reactors. In biomaterials, this will prevent the failure of these materials, and then the manufacture of aeroplanes or aircrafts. This will also help in preventing their failure. So the first step of selecting the materials is knowing their characteristics and its fitness for the purpose. Here are some of the forces that our materials will experience. We have tensile forces, we have compressive forces, we have shear forces, and we have torsion. A strain gauge can be used to measure the tensile forces. In this case, you take your material, you clip it at the top, you clip it at the bottom, as shown in the diagram, then the force is applied. We also have shear stress, where shear stress is tau. Tau is equal to force over area, and in this case, the force is applied tangential to our area A0. And finally, we have torsion, which applies rotational force or produces rotational motion. It has been observed that stress and strain have a relationship that is directly proportional, and this is true for low stress levels or strain, and the constant of proportionality between these two is called the modulus of elasticity or Young's modulus, and the typical range for some of materials is given on the slide. On the previous slide, we said stress and strain are directly proportional, and this is true for a certain region, and this region is called elastic deformation and is shown in the figure. Thereafter, when the relationship is no longer linear, this is known as plastic deformation. So elastic deformation is a region where if a force is applied, the material deforms, but when the force is removed, it retains to its original structure. But for plastic deformation, removing the stress does not cause the material to return to its original dimensions, and this is called permanent deformation. The other materials that don't show the linear elastic behavior, even in the non-permanent deformation region, and typically a graph is shown there. So in this case, the modulus is known as tangent or secant modulus, and this modulus is taken at a specified stress level as shown in the figure, where you can take it at sigma 1, that's a specified stress, or at sigma 2, that's also another specified stress. But it has been observed that for most materials, plastic deformation only occurs in 0.0.5 strain. There beyond this point, most of the materials become plastic deformed. It's non-recoverable, or it becomes permanent. And the transition from elastic to plastic deformation is gradual, or is very slow, and it's difficult to easily mark it out. This will be discussed later in the following slide. And at a molecular level, for crystal materials, when we now get to plastic deformation, we're saying the materials are now, the atoms are now breaking and forming new bonds with the neighboring molecules, and once the force is removed, they no longer return to the original positions. But for non-crystalline materials, what's happening is that the bonds are breaking and the material starts flowing, and if the force is continually applied, the material will flow. Another important mechanical property is yield strength. So as we have said earlier, it's difficult to distinguish between elastic deformation and plastic deformation. Hence, this term yield strength is the one that's usually used to describe materials or to characterize material. So we get this term by constructing a line that is parallel to the elastic portion, and by conversion this is set at 0.02, and the point where this line cuts our stress strain curve is called the yielding point, and this is where we get also our yield strength. Some materials have a different graph similar to the one shown on our left, and you will notice that this one has 2 points, the upper yield and the lower yield, and what is normally used is an average or the lower yield. Tensile strength is another point property that is usually quoted, and this happens at a point on our curve where the material finally fractures. But normally the point that is used for design purposes or the property is the yield strength. We can't use the tensile strength because by the time this is reached, our material will have been deformed over and over. Ductility is the next property that you're going to look at, and this is basically the ability of a material to stretch and not deform or fracture, and it's given by this equation. Another property that comes, which is similar to elongation, is percentage reduction, and this is basically a measure of the thinning of our material. Brittle materials are usually considered to be those that fracture at a strain of less than 5%. A comparison is done between a brittle material and a ductile material on the figure on your right. Another property that you have is called resilience. Resilience is the capacity of a material to absorb energy when it is deformed elastically, and then upon unloading to recover this energy, and this is also called elastic energy. The effect of temperature on some of the properties that you looked at is considered in the slide. On the figure on our left, we'll notice that at low temperatures materials become brittle, and this has been reported to be one of the causes why the Titanic sank. On the figure on the right, you'll notice that yield strength and tensile strength decrease with an increase in temperature, or at least ductility is the one that increases, or elongation increases, and that's why we sometimes do most of our work at high temperatures. May it be working our material, our metals, we do it at high temperatures. May it be extruding plastic or any polymers, this is done at high temperatures because at those temperatures they are more ductile. And then we have the concept of true strain and stress and strain. And previously we had in the engineering stress, we assume that A remains constant, which is not true as shown in the diagram. So true stress becomes the force at the actual area. The same thing with the strain, it becomes a change of length over the actual length, which when integrated we get that. Here is a comparison of a diagram showing true stress and engineering stress versus true strain versus engineering strain. You notice that the true stress or strain continues until the fracture. Generally, true strain or stress have no application in structural applications. When necking begins, our components is grossly deformed for its intended use. So normally as engineers dealing with material processing, we require the data that relates to true stress and strain. The last property that you're going to look at is hardness of material. Hardness of material cannot be defined precisely. Depending on context, it might represent resistance to scratching, or qualitative measure of the strength of a material. And please do further reading on this property. The fig shows some of the comparisons for hardness test and where it's appropriate. This slide summarizes everything that you have covered. Make sure you are comfortable in calculating each and every term that is on this slide and you understand what the definition of the term is.